The next system is SkeletonHunter, and the presenter is Wei Liu. He's a graduated PhD from the School of Software in Tsinghua University. His research interests include data center networks and AI infra. Please.
Yeah. Okay, thanks for the introduction, and good morning, everyone. Today, I'm going to present our work, SkeletonHunter, a system designed to diagnose and localize network failures in containerized large model training. This is a joint work with the colleagues from Tsinghua University, Alibaba Cloud, and UIUC. So large model training is emerging as an important business for today's cloud service providers, or CSP for short. This is because the training process of today's large models always require massive computing resources and networking resources and significant infrastructure supports. For example, training large models like GPT-3 or Llama 3 involves hundreds to thousands of GPUs, lasting for weeks to months. To train a large model, users can launch a training task through either physical clusters or container clusters. While a physical cluster is highly customizable for users, it requires the users to have professional experiences on configuring and coordinating the machines, GPUs, and RNX. Also, it's not flexible enough on scaling and always incur high operational costs. In contrast, containerized large model training has now become popular given its lightweight and high flexibility. Users can launch training tasks with different numbers of GPUs and RNX on demand. In this way, it's more cost-efficient and widely adopted by common users. As a major CSP, we have been operating a large-scale, multi-tenant, large model training cloud for over 3 years. It is equipped with 40,000 RNX and 40,000 GPUs, and has served over 5 million large model training tasks from users. As you can see, the architecture of our containerized model training infrastructure is based on an overlay network, where containers can be created and allocated with RNX and GPUs elastically. Our underlay network is based on Alibaba HPN, which is specially optimized for AI workloads. Under such a large scale, reliable networking is crucial for service quality, particularly the connectivity among the training nodes. This is because the training nodes GPUs should be connected under a low latency, high bandwidth networks, either intra-host or inter-host networks for high performance training data exchanging. Also, large model training is highly synchronized. Each training step requires all workers to exchange gradients simultaneously. Even a minor network issue like 1 millisecond latency increase can slow down training by 20%. A failure lasts for more than 4 seconds can cause the entire training job to fail and finally causes a substantial financial loss to our customers. Unfortunately, pinpointing network connectivity issues is not an easy job in large-scale containerized large model training scenario. This is just like pinpointing network issues in traditional data centers is not easy, while model training workloads further add to the difficulty. The difficulty comes from threefold reasons based on our operational experiences. They are high dynamics of containers, endpoint-induced complexity, and the interplay between the overlay and underlay networks. Let me explain in detail. First, containers are highly dynamic. Our production data show that over 50% of the training containers last for less than 60 minutes, while containers with higher end configurations can have a longer lifetime. We also noticed that even containers within the same training task can start up minutes apart due to resource scheduling delays in different hosts. And the longest delay can last for 10 minutes. All the above container dynamics make the network topology change frequently, making it difficult to keep continuous monitoring. That's the challenge one. We need fast probing mechanisms on such high dynamic network topologies. The second challenge is the end-to-end induced complexity. Each container can bind to multiple RNX endpoints, often 8, to support different parallelism strategies like tensor parallelisms and pipeline parallelisms. This also adds to the difficulty of connectivity monitoring. And thirdly, to support multi-tenancy, we use overlay networks like VXLAN on top of physical underlay. This introduces virtual switches, flow tables, and SRIOV virtual functions. On average, each host has 40 flow tables entries in production, and some can have over 9,000. This complexity makes it hard to isolate whether a failure is in the overlay or underlay. So the third challenge is to disentangle this interplay between the overlay and the underlay networks for failure localization. And what is even worse is that these challenges form a multiplicative effect on the connectivity monitoring among training containers. Suppose we have X containers. Each container has bound to Y RNX, and each RNX corresponds to Z virtual network components like flow tables. Then the total number of network components to be examined in each training round is X times Y times Z. For a training job with 1,000 containers, each with 8 RNX, and each RNX corresponds to 16 virtual components, we must monitor over 28,000 network components for per training round in about 20 seconds. This is not feasible for traditional monitoring tools. So to address the above challenges, we performed an in-depth study into the training traffic and found 2 opportunities to effectively reduce the complexity of connectivity monitoring for large model training, containers large model training. First, training traffic has a sparse spatial distributions since training data are exchanged across GPUs with data dependencies. This is derived from the various parallelism strategies used in large model training. For example, a large model can be split into multiple GPUs to avoid the model size exceeds the capacity of a single GPU. This is called tensor parallelism, or TP for short. Then, different layers of a model can be further split into multiple hosts to enable pipeline training. This is called pipeline parallelism, or PP for short. Similarly, we can divide the input data into multiple batches to enable concurrent training. This is called data parallelism, or DP for short. So after the training iteration, different DP groups will exchange the parameter values to synchronize gradients. And furthermore, today's real-optimized data center topologies for AI workloads like HP and Alibaba also result in sparse traffic distributions. Any intra-host cross-rail communications will be transformed into intra-host communications in the same network rail. So actually, the network connectivity only happens at the same rank of RNX across different hosts. So the above parallelism strategies and data center topologies form a unique traffic distribution. Here we show the traffic metrics of the RNX for different models. We can see that most GPUs and the corresponding RNX do not require connections, and each DP level presents repeated connection patterns. Apart from the temporal feature, the spatial feature, training traffic is also periodic in the time domain. We noticed that each training iteration ends with a burst of gradient synchronization, followed by idle period, as shown in the figure. These spatial and temporal characteristics of the containerized model training traffic all get us to distinguish the role of the RNX of each containers so that we can minimize the, optimize the connectivity provisioning process. And we present SkeletonHunter, a system that enables efficient and accurate detection of network issues for our in-production containerized model training services. Our key idea is to infer the traffic skeletons, which are composed of a crucial set of network paths consistently traversed in large model training to reduce monitoring complexity. SkeletonHunter is inspired by the pin mesh architecture, but tailored for training workloads. It consists of 3 components: a controller that generates the pin list or pin targets, and the agents deployed on each host that perform actual probing, and an analyzer that detects anomaly and updates the traffic skeletons for the training job. So to infer the traffic skeletons of a training job, the generation of the pin list for each container is in a phased manner. During the preloading phase, we remove pin targets from an all-to-all pin list that are not in the same network rail, which reduces the scale of pin list to 1/8 of the original all-to-all pin list. The next phase is the initialization phase, which aims to mitigate the probable false probings due to different startup times of the containers. To this end, after receiving the pin list from the controller, the agent on each container does not ping the others until some other containers register themselves after their creation. In this way, we minimize the false alarms on the network connectivity issues among the containers that have not been created in the same training task. At runtime, we further minimize the pin targets with the inferred tracked skeletons. Our key observation is that ANICs in the same rank position across different DPs have the same burst patterns in traffic. For example, the traffic bursts of ANICs A and B are similar, and ANICs C and D are also similar, since they are in the same rank position of different DPs. We use short-term Fourier transform to extract the frequency features of these traffic bursts for each ANIC, and we cluster the ANICs with similar patterns to infer their DP groups. In order to make the clustering process more accurate and interpretable, we added the following constraints to the clustering process. First, the number of requested GPUs are only confined to a limited set of values. So we added the constraints like each DP group should have the same number of ANICs, and the multiplication of DP, TP, and PP should be equal to the size of the training cluster. Besides, each ANIC in the same host should belong to a different DP group, since the intra-host GPU communications are handled by NVLink or PCIe links. In terms of PP, we infer their different levels based on time-shifted send and receive activity among the ANICs. And finally, we can infer the TP groups where ANICs have no network connectivity for intra-host communications. So in this way, we can infer which ANICs belong to which person group, and therefore recover the traffic skeletons for a large model training task. We then remove the pin tags that are not in the traffic skeletons, and it further helps us reduce another 80% of pin list. We can eventually get the final pin list that is only around 5% of the original pin list. After connecting the end-to-end latency data from the agent with the optimized pin list, we detect connectivity anomaly among the ANICs and containers from the data using a statistical method, including the short-term and the long-term detections. Short-term detection uses a sliding window of 30 seconds and applies local outlier factor to latency percentiles for detecting latency changes. And the long-term detection uses a 30-minute time window and a statistical test against a log-normal distribution model to catch gradual degradations in the end-to-end latency. Once a connectivity failure or high latency is detected, we use optimistic disentanglement to localize it. Our key insight is that the root causes at overlay and underlay layers are usually software and hardware related, respectively, which will not propagate to each other. So they can be checked separately. For the underlay, we leverage a faulting-based failure localization mechanism to fault for the links that are always that always lie between the connectivity failure endpoints. For the overlay, we perform flow table reachability tests to examine whether there is an error in the forwarding rules. If both seem healthy, we fall back to manual inspection of ionic flow tables. SkeletonHunter has been running in our production workload for over a year. It monitors over 5,700 physical hosts and 40,000 ionics. Every day, it connects and analyzes over 1 billion latency measurements, providing real-time visibility into the network health. SkeletonHunter has detected over 4,000 network failures with high accuracy. It correctly localized 95% of them to specific 40 components. After fixing this issue, the monthly failure rate dropped by 99%. The design of infrared traffic skeletons significantly helps us reduce the detection complexity. On average, SkeletonHunter can finish a probing round in 8 seconds, which is much shorter than a training round for large models. So let me conclude our work. We are the first to pinpoint the real-world challenges against reliable network support for large-scale containerized model training, as well as their multiplicative effect on troubleshooting the connectivity issues. We propose SkeletonHunter, a container network monitoring and diagnosis system that leverages the unique traffic patterns of large model training to accurately and efficiently pinpoint the connectivity issues. SkeletonHunter has been deployed in our production container network and has shown its efficacy in network failure detection and localization. That's all. Thanks for your attention, and I'm ready for Q&A.
Thank you. Any questions from the audience?
Great talk, thank you a lot. So I saw in your paper you list a pretty nice table of the problems that you find with the system. So could you briefly comment on a bit kind of those gray failures or slow degradation thanks to the 30-minute long-term kind of anomaly detection system that you put there? Thank you.
Yeah. So actually, we have encountered a number of network failures during our operation on our containerized large model training services. And one of the most, or say, the frequent issues is that we find that the ionics actually act as a black box for us, and sometimes their behaviors is not expected as expected. So, for example, when we offload some flow tables, the flow tables offloaded to the ionic can be inconsistent with what we see at the control plane. So the network performance significantly degrades when the flow table in the ionic is missing. So that's in my viewpoint, it's most impressive network issue that we have encountered. Yeah.
Okay. Any more questions? I think we have time for maybe 2. Okay. Let me ask one. So in the last few slides, you mentioned about the evaluations and the production experience. You mentioned that there's a 98% accuracy. So could you talk more about in 2% where you fail?
Yeah. Actually, there may be not monitoring. There may not exist a monitoring system that can detect or localize all the network failures in production. And some of the false detection or failure localization derived from our, for example, we deploy an agent, and some of the agents can crash in production. And then we will find that the end-to-end connectivity it also fails, just because the agent fails. Yeah, and that's one of the inaccuracy comes from. Yeah.
Okay. No more questions from the audience? Yeah, let me ask more about the actual workload. So from what I see, it's not all large language model training. There could be other types of models in the cluster as well.
Yeah. This is not only for large models. It can be used for any deep learning model training. Yeah.
Okay, so I ask this because it's weird because I thought one tenant per host is more traditional or more popular for large model training. But you mentioned somewhere in your slides that there's a multiplicative complexity. There could be multiple tenants for a single RNIC. So that seems weird to me. But thank you. Yeah, let's thank the speakers again. And